we're going to talk about more about decomposing functions into different parts. Okay, so I'm going to review a little bit about what happened in the vibrating string problem. So let me talk about the objectives. So understanding boundary value ODEs. So initial value ODEs and Eigenfunctions come into play. Okay, so I'll review this a little bit. So these are the problems from section 3.9. I think you might have done, depending on who you might have had some boundary value problems in your ODEs class. I don't think anyone maybe it wasn't so motivated as to why you were doing them, and this is one of the big reasons for this PD application. So another thing is this understanding PDEs. So this is what okay, so this is another thing. So this was section, I guess this was section 9.4 was what I was talking about with I said section 6, but this is section 9.4 with the just plugging in certain functions in the PDEs and seeing that they're a solution, okay? And lastly, so I want to, this is the most important part, is understanding I guess inner product spaces, but how norms and inner products work. For function spaces. And I'm going to get to this in a second. So this is section 12.1. Okay? Also, so the vibrating string problem, so the other thing is that we have this, we have one more objective which is listed later in the objectives, which is knowing how to solve the boundary value problem for these standing waves, which is something that we talked about decomposing into constituent parts. And now you guys are pretty much in a position to start solving those problems. So the boundary value problem for the wave equation. Okay, and this is, I guess, this is section 13.4. So I skipped ahead in order to motivate section 12. Okay, and so this is for zero boundary. This is like we have our string and we're fixing the string. There's other problems where you can have the string doing all sorts of crazy things at the side, but we'll talk about that in a bit. Okay, so like if you're waving the string and then what happens on the other side. Okay, all right, and so the plan, okay, so I need to explain what some words mean. I need to explain these words, you know, completeness, so what orthogonality means, so explain these words for these functions that these eigenfunction expansions. Okay, so I want to kind of present what we did yesterday. So I'm going to review what we did, or last time, in analogy with what we did for ODEs. Okay, so let's do this. So the analogy in PDEs. Okay, so so ODEs. We looked at things like dy dt is equal to ay. All right. Let's see. Maybe I'll need to create some space here. Right. And what was the strategy? The strategy was to expand. So the strategy is that we expanded. So when this matrix is diagonalizable and has a basis of eigenvectors, right, we expand in terms of a basis eigenvectors. Okay, and what we write y, which is a function of t, as w1t c1 plus wnt cn. Okay, and this is just a sum, I guess, of wk c k for k is equal to 1 up to n. Okay, so these guys here are the eigenvectors. Okay. Step 2, can you guys see down here? Right. Step 2 was we decoupled the system of differential equations. Okay, so we solve mode by mode, right? Mode by mode. By mode by mode. Okay, well, by eigenvector by eigenvector. Okay, and we got these differential equations. Wk prime of t was equal to lambda k wk of t. So these guys, wk here. Okay, and these were easy to solve, right? So we had these very simple differential equations that resulted from expanding in terms of a basis of eigenvectors. Okay, so we had this step here, and then we have this step here. All right, so maybe I can try and separate this. All right, okay, and so this is how we built up a solution of an ordinary differential equation. Cool? Okay. All right, and so in our PDE, okay, so for PDE, okay, and this was our particular PDE, we had here d squared u dt squared is equal to d squared u dx squared. So u is a function of u of x and t. And this was a simplification of this wave equation, right? So this is the wave equation with the constants equal to 1, right? So this, we had a v squared here or something like that, okay? And so we think of this thing as a applied to u, where a is d squared dx squared. Okay, so it's kind of like this situation where we have something on this side, and then we have an operator applying to our function here. So what we do is we expand. Okay, so also, okay, so another thing. Let me just make a little remark here. We assume that these u's satisfies boundary conditions. All right, so this makes so this thing's operating on some u's that satisfy some conditions. Okay, and so so then what do we do? Okay, so step 1, right, was we expand in terms of eigenfunctions. Okay, it's not exactly, I guess, eigenfunctions for. Well, I guess it is eigenfunctions for this operator, right? So here, right, we write the solution u was a sum from n is equal to 1 up to infinity of, well, we can call this wnt cnx. Okay? So yesterday we called this thing, this was tnt, and I put some coefficients in here yesterday, but I'm just going to absorb the coefficients into this. And this was xnx, so this was yesterday. Right, so this was, this is also, this is sine pi n x. Okay, and this was for n is equal to 1 up to infinity. Okay, so this is what we called the. Is it clear what I mean by this was what we called this yesterday, and this is what we, or yeah, yesterday, but the previous class. Okay. Okay, so these were our eigenfunctions. Okay, so these guys, these are our eigenfunctions. Okay, and then these are like our coefficients. So these are like, so now we're expanding, and these things play the role of these things. These depend on time. Okay, so again, we're just expanding in terms of eigenfunctions instead of eigenvectors. Okay, and that decouples the equation, right? So in step 2, we solve for the coefficients mode by mode. Okay, and what here we'll have the same, we'll have a similar situation. So we have Wn prime prime t is equal to lambda n Wn of t. Okay, so this was the other equation that we got from separation of variables. Okay, and so lambda of n we solved was equal to negative n pi squared. Okay, and so the interval here, I guess, was the interval 0 to 1, right? So so here, let me I guess make a remark up at the top here. Okay, so I'll write out the full problem again. Okay, but this was the idea. Okay, so this is the kind of analogy that I want to present, so you can kind of keep in your head what's going on. Okay, so so let's go back to our particular problem. All right, and so we had this equation here. So this was our, dt here. And then we had x was an element of the interval 0 to 1, and t was greater than or equal to 0. Okay, so this was the main part. And then we had the boundary conditions. So the boundary conditions said that, so the endpoints are going to be 0. So that fixes them at the end of the guitar. Okay? All right. And then we had initial conditions. And I didn't really talk about the initial conditions, okay? And I punted that to today, which is something that I'm going to talk about more. So we could have something like, so u of x 0, or u of x 0, so at time 0, it's equal to f of x, and u of t x 0 is equal to g of x. Yesterday, or last class, here, we had that we had f of x was equal to f of x was equal to u 0 of x bar, right? And then g of x was, say, equal to 0. All right? The other thing that I wanted to say is the other option, so there's another option. So there are other options for this. Right? You could try to do other things. It turns out this is the thing that you want to do. I'll say a little bit about that in a second. But you could try, you could try saying something like x0 is equal to g of x. Okay? Or there's loads of conditions where you can kind of combine these things and do all sorts of things. Okay? But the name of the game is always that you get a general solution, right? Or you get some sort of general solution, and then you plug that solution into your boundary conditions to see what pops out. Okay? Just like we do when you solve, like in the quiz, at the end of the quiz, I was like, okay, if you have these initial conditions, right, how do you solve for the coefficients? Well, you plug in your initial conditions, right, and then you get some equations. Okay? It's kind of the same idea here. All right? We need to talk about what plug in means in this context, but it remains to be, it turns out to be the same thing, okay? So, okay. So then we talked about this separation of variables technique, okay? So separation of variables was how we got this thing, okay? So, okay, so what we did is we did u of xt was equal to x of x, t of t. All right, and then we had x prime prime is equal to x, and t prime prime is equal to lambda t. So those were the two conditions that we get. Okay, and from this, so from the boundary value ODE, for capital X, so that is this thing, we derived this equation. And then we had x of 0 is equal to 0 and x of 1 is equal to 0. We get eigenvalues and eigenvalues. Okay, and so let me say what these are. So those conditions, so doing this on this type of solution gives this. All right? And when you plug that in, we ended up finding out what these lambda n's could be. So it imposed a restriction. We got lambda n is equal to negative n pi squared for n is equal to 1, 2, 3, so on and so forth. Okay? And then we got that xn of x only, so this is sine of n pi x. Okay? Okay. So the question remains is how to deal with the initial conditions. So okay, and so I thought this is very sneaky. Let me just say that this idea of decomposing into eigenfunctions, right? So that was due to Euler, right? It's very old, this vibrating string problem. The solution, this idea of doing decomposing into the separation of variables and doing that sum, that's due to Euler, right? And then up until the late 1900s, early 2000s, people have been figuring out, like, when does it work, right? So, so this was a very big, piece of math, right? And it essentially, the problems around when this thing works, led to the development of like analysis, and so this is why the class is applied analysis, right? And harmonic analysis and things like this. Okay, so this is dealing with this solutions of the vibrating string problem, or in generalizations of it, lead to the subject called harmonic analysis. Okay, so let's sort out. So the to-do is to sort out the initial conditions. So I'm going to give you Euler's formula, and then and then I guess give a full solution to the vibrating string problem. All right. All right. So, okay. So let me just look at these initial conditions. So we had two types of conditions. We had this condition and this condition. Let's look at that. All right. So there was two types that we mentioned, right? So we had this one, right, where we had or we had this one, okay? Okay. I'm going to explain why the right-hand one is silly, right? So here, this thing, this is specifying the slope of the initial condition, initial displacement. So again, so what we're doing here is we're taking our guitar, and then we're raising it to a certain height. Maybe we could have called this thing y. So other books, they call this displacement y. So it's the displacement from the y-axis, or from, and then you let it go, okay? So what this is doing is this thing here is specifying, this is specifying the displacement, this is specifying the slope. So this one's really no good, right? This one's, because really, this should be determined from this, okay? All right. This one here specifies the initial displacement. So these guys here. In that example of that function that I gave was like this pyramid thing, right? A single pyramid. Okay, and then this one here is the velocity. So initial velocity of the string, right, at a point x. Okay, so it's like how much you're strumming it, I guess. Okay, so this is the type of thing. This is the one we want. All right. So, all right. So this is what we have. Okay? And so, so now I need to make a decision about so I need to tell you okay, so I need to tell you about inner products. Okay? We need to talk about inner products for this to work. And okay, so let me just start. Let me tell you the problem. Okay, let's go with this problem. All right. Okay. Okay, so let's see what happens when we plug in our initial conditions into our equation. Okay? Into the following equation, right? So we have the following. So we have u of xt. So this is the sum from n is equal to 1 up to infinity of tnt xn x. Okay? So, so this equation here, in u tx0, so we have these two things, these two functions here. So this tells us the following, that so let's see what ux0 is. So let's just compute both sides. So the left-hand side of this side, okay? So this is u of x0. This is the sum from n is equal to 1 up to infinity of tn0 xn x. Okay, ut x0 is equal to the sum from n is equal to 1 up to infinity of tn prime 0 xn x. You guys agree with that? Okay, and so now let's look at the right-hand side. So we're looking at the left-hand side and right-hand side of this. Okay, so we have left-hand side of this thing, star. Okay, and these are the initial conditions. So we have this thing. Okay, and this is equal to, okay, the right-hand side. So these were f of x and g of x. Okay, so this is supposed to be equal to f of x, and this is supposed to be equal to g of x. All right, and so the trick that Euler did, so this is the cheating trick. Okay, so here, so this is what Euler does. Okay, so that this function here, we pretend that this function looks like 1 to infinity of an xn x. And this one's the sum of n is equal to 1 up to infinity of bn xn x. Okay, for some sequence of numbers, an and bn. Right? So we pretend that we can write it like this. Okay? And if we can pretend like we can do this, so it turns out we will be able to, right? So if expand f of x and g of x in terms of the eigenfunctions xn of x, right? Then what do we get? So then we get equations. We get these equations from n is equal to 1 up to infinity of tn0 xn of x. And this is the sum of an xn of x. All right, and then we have the sum of n is equal to 1 up to infinity of tn prime of 0 xn x is equal to the sum here, n is equal to 1 up to infinity of bn xn of x. Does that make sense how I got those equations, right? So I just set these two things equal to each other. So first step, okay, so let's label this. We need to remember this somehow. So let's, so maybe we should label this. So let's say this is trick 1. Okay, the first trick 1 is this eigenfunction expansion. Okay, trick 2 okay, well, let's say that the coefficients of each of these things are equal. and Bn are okay, and then we can just equate coefficients. Okay, so this is trick 1, and this is trick 2, right? If we have trick 1 and trick 2, we can get the solution of the vibrating string problem. So provided do and trick 2, we get the following initial value problem. Pi n squared this, and then we get Tn0. Okay, and this thing here, this is just an ODE, right, with 2 initial conditions. An ODE. Which we know how to solve. Okay, that's a lot of writing. All right. Okay. Okay, so do you guys get kind of like what what's going on? Okay, so like we have this one, we solved for the x's, and now we'll be able to solve for the t's provided like we can cheat like this. And this was like very controversial, right? So like I think it was kind of like I think like the Riemann hypothesis of the time was like to figure out the vibrating string problem. Okay, so this was like their very big math problem back in the day. And then when someone said, oh, you can just write the functions like this, people were like, but why? And then it became like a thing to figure out like when you can do this. All right. So let's talk about and I'll tell you what Euler did. All right. So I guess right. This is the end of class, huh? So okay. So next time. The way to do this, the way to actually get those coefficients, right, is to use inner products, right? And so I have to generalize some linear algebra, right, for function spaces rather than just vectors. I mean, function spaces are vectors, but we needed to do some sort of infinite dimensional version of dot products, okay? And that's the way that we're going to solve for those coefficients. All right, and so I guess we'll do that next time.